next presenter, Dr. Shibab Ibrahim, to talk about waste glass powder and how that can be introduced in ground improvement. This will be our last presentation in the morning. And after that, I will wrap up the talks and we can go for lunch and we will come back for the session 2. So, thank you, Ibrahim.
Welcome to my presentation. This is soil stabilization we have with Geopolymer using glass powder. Now that the topic divided into 3 sessions, I'll go very briefly over them, so we'll only focus on the experiment that we have. So, as we all know, the soil improvement can be done with different procedures, whether changing the soil or mechanically, or it can be done with the chemical stabilization or additives that we can add to the soil to improve the engineering property of the soil. Now, as we all know, lime and cement has been used in several decades or even past in a very old time for stabilization. And the mechanism of working the lime, it rises the pH value of the pore water, which later releases the aluminum silica from the soil, going to reactions for cementing property. On the other hand, cement is known that to hydrate with react with water to have calcium silicates, and then sodium hydroxide or calcium hydroxide will go further reaction with the soil, alumina, and silica. Those are well-known mechanisms for the 2 additives in soil stabilization. And we all know about the harmful or the environmental impacts of calcium-based additive, which is cement and lime, which mainly the carbon decomposition that leads to greenhouse gases, and then beside that, nitric oxide, which leads to acid rain, and some other durability problems, which I'm not going to focus on because our study is still on the preliminary stage, so I cannot decide on the durability issue of the product that we have here. Now, many research was going on the replacing the cement with organic material such as fly ash and DGBS in order to stabilize soil with a lower energy or lower environmental impact that's available. So the geopolymerization process in soil stabilization is kind of new in the past. Well, the geopolymerization is not new. Geopolymer is not new buying. It's been there since 1978, but in the soil stabilization, it's the last 2 decades, some research is going on using different classes of pozzolanic material in order to stabilize soil. And I have mentioned that it has a superior quality or properties over the traditional cement and lime stabilization. Now, geopolymer is considered as an organic material which comes in the reaction of aluminum and silica, which are available in soil, but in alkali media. So there is a requirement for alkali media in order for this process to be happening, which also considered to be somehow naturally occurring process. In one of the publications by Dr. Arya, they mentioned that it's kind of a process that's happening with weathering and chemical reactions in nature. But it's still early to decide with the final product to see how does it behave in the soil. So this is a schematic representation of the process that we have. So the alkali we have the solution and condensation goes into the hardening process, which is the 3D gel we have with the polymer. Now, on the other side of the project that we have is waste glass that's increasing over the last 10 years in Europe, which is a newest data I got it, it's 34 kilograms per capita of waste glass we have. And the main glass that we have is soda lime, which is mainly the bottles or the one that we have. Now, in some countries, they use recycling of those glasses, but they have limited due to the coloring purposes. Unfortunately, I'm not aware of Cyprus. I have even data on the glass. Even in Turkey, we got some data. It's 1,200 tons per year, and instead of not filling, some goes for recycling, but we're not sure about the full data in Turkey. So this is one of the emerging things that we're looking for glass, and mainly it's silica. So our study here is focusing on the glass, which is the bottle colored one, which is highly silica, 70% silica, and then we have some soda ash because the bottle we have using is soda ash, and the soil that we have considerably clay soil. Our focus is on the optimal moisture content here. However, there are some limitations to the study, which for the future research we can contribute more into the project. So we have some proportions that we have. So that the mix design has been done, all of them come up with the same optimal moisture content, which is based on the soil that we have it. So we didn't go into different optimal moisture content by adding those things. As we expected that the optimal moisture content can change when you have a geopolymerization. There are things that go in that the density changes, the porosity changes, or the material that we add in there, it changes the structure of the soil that we have. But we kept the optimal moisture content based on the soil that we have. So the things that we have here, or I should mention it, we didn't go to take the unconfined compressive strengths at the optimal moisture content. Since geopolymerization required time in order to gain strengths, so the tests that we've done them at the exposed sample, there are the dry condition, or let's say that in the room temperature, or we have two of them. One is the room temperature left there for 70 to 80s, one in the curing 60. So the things that we'll be discussing here are mainly focusing on the room temperature, since we don't want to use any or heating basically, or we cannot even use heat in the soil stabilization. So it's only done to see that increase in the strengths over age. So the one that we have it here, the effect of curing, we will see that the early ages, 7 days, 28 days, a rapid increase we have over age. But the things that we're interested here, the strengths that we gained in the process. Well, we can see this is the soil, which is without cement, and we have one control which has 10% cement to compare with the result that we have. Since they are a dry condition, the way we have a higher strength. I'm sure that this isn't for those in soil stabilization, you see that this is high strength, but because they are dry, not at optimal moisture content, that's why I have these results here. For the soil, it's 2.54 megapascal, it's high strength basically, because it's a dry state. We left them at the room temperature for the 28s. However, on the other side, I have it here for the room temperature, 13 megapascal is high strength for soil stabilization. That's why we might even shift the idea of this one with different perspective, not just for soil stabilization, or maybe in the future research we will go further deeper to see in the porosity, this because all of them are compacted. And so we have mechanically, we have also chemically stabilization. So I might even go for more porosity to see we can drop this one down with a higher porosity in the future. So the things that we have with molarity is one of the aspects in geopolymerization that we tried it here. It's clear in most of the cases 10 molarity will be more than enough. In the future research, we might even reduce this one because of the glass already has high sodium inside, which may leach out and be used for the geopolymerization. This is one of the drawbacks in geopolymer we have because it's not user-friendly material. On the other side, sodium silicate is a user-friendly material, but this is one of the drawbacks that we have in the future research. We can focus on the alternative or maybe ways to be used for activation. Sodium silicate, as we said, that is one of the things that help us in the room curing, increases the compressive strength in the without going to the further curing stage that we have. What we did here, we used the optimum cases for the study and we did direct shift tests. And this is what we've seen here, a dramatic increase in the shear properties of the material, which you can see there from 76, 10% cement to 697, which is the cohesiveness, and the angle of internal friction has increased dramatically there. This is something that we can focus later to do more research on that one, to see how it behaves or the brittleness of the material. That will be a different aspect of the things that we have. So on the conclusion that we have it here, we already know that curing or in cycles basically because of the heat. So it might heat here, we can tighten the temperature for T, basically for cycles in the condition that increase the reaction and to see how does it work in different stages, whether winter or summer. Well, ambient temperature that we did was providing and gaining strength over age. So that might be another aspect that for the longer period to see how far the strength is going to go. That's something we can study. Well, not only the strength will be the things that we have. Durability is one of the issues that we should encounter to see over age what will happen in the sulfate attack and the acid attacks, or to see how this material will behave with age. So we provided that 10 molarity will be enough for the solution that we have here. You already know that sodium silicate is one of the things that it's important for us in order to bring the things in the curing condition rather than to go for the higher condition that we have here. And we're also seeing some of the shear strengths, and this research is still ongoing, so we still have some things to contribute to it, and further things are coming. And the recommendation from yours will be, I'll be glad to get some recommendation over that project. Thanks for your patience.
Thank you, and that was the last of Dr. Ibrahim. If you are convinced, I appreciate. So that was the last of our presentations for